limits and continuities. So let's begin considering this. First, we do this in R. First, we will take our metric space to be simply R with its usual absolute value. Okay? Let's recall what is continuity on the real number line. And you may make the following statement. So, first let's recall what limits are. So we say that limit as x goes to c of f of x is equal to L. By definition, it's if for any epsilon bigger than 0, there is a delta bigger than 0 such that the absolute value of f of x minus L is less than epsilon whenever the absolute value of x minus a is less than delta and bigger than 0. This means puncture neighborhood. We don't want x to equal to a. That's what you did in calculus. Good? Now, this definition might be better stated in the following way, right? If we, instead of saying this phrase, you just might as well say if there is a delta epsilon function. You understand what I mean by delta epsilon function? So in the limit, what we're saying is that I'm plugging into f a bunch of c-like numbers. So number that is not really c, but c-like, right? Maybe c minus 0.00001. That's one example of a c-like number. So this is saying as the numbers are close in proximity, as they get closer and closer in proximity to c, the outputs are getting L-like. In other words, the outputs are closer and closer in proximity to the number L. The way I imagine it is like a water cannon. That's what I usually imagine it. So you have a water cannon, you slide it over the point C, and then what you have here is this is your function f, and this is the wall. So your target is to hit L, and what happens is that you can control the input stream. You can control the input stream around C, and that's what delta is doing. Delta, this thing is, like you're a plumber, you are closing in the pipe. You're making it either very narrow or wide. So in general, you will make it, so this here is C minus delta epsilon, C plus delta epsilon. That's this volt function. Give me a second, I'll write with you. And then you can see that this current you feed in. You are not allowed to feed in C. That's why we have absolute value of x minus a bigger than 0. That means that we kind of put a lid on C. We're not allowed to put it in. We feed it into this mechanism, and as we feed it in this mechanism, depending where the point came from, so all this interval is what I consider C-like inputs. Those C-like inputs are going to squirt. Some go here, some go here, some go here. Right? So they are squirting, and what happens is that what's the epsilon supposed to represent? The epsilon is supposed to represent the widest size of the state that I'm allowed, right? So this is L minus epsilon. This here is L plus epsilon. So what this function is doing, it tells you close in the lid, the current will be very narrow. It will be very thinly sprinkled around the point L. Do you understand the idea? That's what delta epsilon is. That's what I mean if there exists a delta epsilon function. In other words, if you can tell me how thin the current around C should be for the stain to be of radius no more than whatever epsilon you have. And if you can do it for any epsilon, the function has a limit at L.
Why is it x minus a and not x minus c?
Oh, both, you are right. I just like A so often that I forget about such things. I automatically write A rather than C. Thank you for noticing. Now it's good. So you understand this idea? That's a picture that you have. You are just describing a water gun. That's delta epsilon. Now, that's one definition. Let's call it definition I. Now we might have another attempt to define limit at L. We might say that for any x sub n going to C with the explicit assumption that no xn is ever equal to C, we have that f of xn will go to L. Okay? Now this means in terms of sequences. I'm saying that I can take any sequence whose terms approach C. Then if I look at the images of each of those terms in the sequence, they will approach L. Okay? So that's the second characterization that we have so far. And then the third characterization is the sequence for any xn going to C, and we make the requirement that xn never equals to C because we're not plugging C. We have that the sequence f of xn converges to something. And I mean to something. I don't even specify to what it converges. Good? So all those three conditions are equivalent. Remark? All three conditions are equivalent. I don't know, maybe I should show why. I kind of don't want to, but let's try. Let's see that 1 implies condition 2. Okay? Does 1 imply condition 2? So I have the delta epsilon definition. Notice that the delta epsilon definition, just what it does, it picks a full punctured neighborhood. It picks a whole lot of points. Okay? So what do I know? So what you do is, if xn goes to C, with the assumption that xn never equals to C, then for any open neighborhood of radius delta around C minus the point C, that's what I call a punctured neighborhood. You see, it's a full neighborhood, but I remove C because I don't need it. Yes, please?
Is there any reason why you're removing C?
Yes, because when you do limits, remember when you do just limits, you are not allowed to plug in the value. You see the difference between a limit and plugging in the value, the difference between limit as x goes to C and f of C might not even be defined or might be quite different from the limit. If the function is not continuous, f of C is not the same as limit as x goes to C. Okay? Usually in calculus you see that when you divide by 0. So for example, if you have maybe something like x squared divided by x, and I try to plug in 0. X squared, it's 0 squared divided by 0 undefined. I cannot plug in 0. But if I take limit, I can cancel out the denominator. That's what happens. Remember, right? X squared over x because x is not 0 but only 0 like, it approaches 0, I can cancel out the x, and what I have is it's really limit of x going to 0 of x, which is 0. So that's how it comes in calculus. It can come in much worse bundles. In other words, not as simple, but that was the idea that led Newton. Newton had to consider this to avoid, in calculating instantaneous velocity, avoid dividing by 0. That's really one example, right? So that's why we consider the punctured neighborhood. For any this is called punctured neighborhood. So I'm sure I made misspells in neighborhood. I can never spell it right. And there is a British spelling which is different from the American one. So does it look right? Thank God. So this is a punctured neighborhood. What do we know? We know that xn belongs to this ball of radius delta around c minus c for all n larger than some n of delta. This n depends on delta, right? So it depends on the particular sequence and on delta, if you want, right? Maybe I should say the n depends on the particular sequence. I won't bother. So it just depends on delta. So what does it mean? It means that f of xn minus L will be less than epsilon. In other words, I'm being a bit loose in my notation. I hope that you see the logic perfectly, crisply clear. What's the logic? If a sequence goes to C, it has to enter those blue boundaries of my pipe. Now everything in that pipe is mapped within epsilon. So the sequence in particular is mapped to where I need it to go. In other words, this definition seems to be much stronger because it doesn't really map a sequence, it maps uncountably many points at the same time. It maps them to within a puddle of size epsilon centered at L. Yes? So, in fact, when I do the proof, it's just, again, you can be a bit lazy. Condition 1 appears much stronger. So now let's consider what happens if I have condition 2. So now I'm going to take condition 2 and show that it implies condition 3. So condition 2 means I assume that whenever I have a sequence that converges to C, its image under F will converge to L. So how do I know that the sequence of f of xn always converges to something? Well, that's obvious, right? That's immediate. What do you write? Right? Of course, the sequence converges to what? If I have the second condition, it's stronger than the third, it seems, right? Because f of xn converges to L, so surely it will converge to something. Namely, in this case, all the time it will converge to L. Good? Now let's try to show that 3 implies 1. Just kind of close the loop. 3 implies 1. That's maybe the hardest to see, because 3 looks like the weakest condition and it should imply the strongest condition. In essence, what I'm saying, they're all of equal strength. So 3 implies 1. So assume that no delta epsilon is possible. Do you understand what I mean by no delta epsilon possible? Condition 1, the definition of limit as you learned it in calculus, tells you what? Tells you that I can have this turret, I can place it over C, that's the function, and if I close the pipe sufficiently, the stream will be as narrow as I want it to be. Tell me how narrow you want it. You want me to make the stain. If you want it to be of radius epsilon or less, I will figure out using this delta how wide to make the pipe, and then I have this. Okay, so assume that no control on the pipe will give you a narrow enough state. So basically, there are things that are always squirting outside of epsilon, always droplets of water falling outside of this interval. So what does it mean? It means that, in particular, it means that if I take delta of let's say 1 over n. So I make, for epsilon I can control it by 1 over n. Delta of 1 over n implies sum xn not equal to c is mapped outside the interval L minus 1 over n, L plus 1 over n. You know, I will do, it would be maybe easier, in other words, the argument might be, I'll write this like this. I'll imply 2 and then 2 implies 1. It's easier to, so outside of this, okay? So what you have is that we have this. So we have the sequence f of xn. F of xn, it does not converge doesn't go to L, but converges to something. So let's say it goes to some number s. You will have to forgive me and erase what I wrote. So, because again, I switched, I said 3 implies 2, but I then still try to talk about delta. So we have 3 goes to, 3 implies 2. So what am I saying is that if the sequence always converges to something, I want to say that it will always converge to the same value, whatever that L will be, okay? The way I wrote it, I think I'll try to recover it, but not worth it. So forgive me for that. Here is how we go about it. So we assume that 3 hold. So what we have is pick xn going to C, where xn not equal to C. So what we then have is that f of xn, according to 3, by condition 3, f of xn will converge to something. Let's call this something. Let's call this something s. Okay, and then I will pick another sequence yn. Going to C, again that yn not equal to C. And what do I get? I get by condition 3 that f of y sub n will converge, maybe not to the same something, to something else, which we can call maybe p. It will converge to some p. You understand what this is saying? This is saying that whatever path you take, you are always arriving somewhere. So, but it doesn't say that you arrive in the same location. So I picked one path, I arrived at S. I picked another path, I arrived at P. How are P and S related? How are P and S related? What do you think? And why? Bart, sorry.
They must be equal.
Yes, they must be equal. You wanted to say?
Does it have to be continuous?
No, we know nothing about anything, any continuity. We are trying to show the equivalence of the three conditions. One, the definition of limit in calculus. Two, the sequential definition of limit. And three, which doesn't even mention what's the point of convergence. Three is the most mysterious.
If it's not continuous, if it's like a... Yeah, if it's not continuous, does it have to equal S?
So P has to be equal to S. So notice that what we can do is claim P equals S. How do we know that P is equal to S? Well, how do you know that? We take one sequence, goes to C, another sequence that goes to C. How can I prove that P must equal to S? Any ideas? Yes?
Because f of x and f of y, the limit as both x and y approach the C should give you the same value.
How do you know? No, that's you're stating what you desire, but how do you know that? Maybe they shouldn't.
Because it's the same function, going to the same point.
Yeah, but also different points in the sequence. That we only have this condition that any sequence, as we go to C, converges to something, right? In other words, here is the statement that think about this analogy. What this is saying is that all roads lead somewhere, and what we want to prove is that they all lead to Rome. All roads lead somewhere, they all lead to Rome. That's what we're trying to get. So one road led me somewhere, another road also led me somewhere. How do I know that somewhere, one somewhere and the other somewhere is the same place?
Well, doesn't the unit step converge to 0 from one end and 1 from the other?
No, I mean, we have no idea. We can just, even in this case, we can just throw the points around, right?
The unit step, right? It goes to 1 or it goes to 0, right? It's 0 and then it becomes 1. So if
you're talking about a particular
a
function.
function called the unit step.
Okay.
If you push from the right side, it's 1 until you hit a point, and then it becomes 0. So if you push
Right.
to the left,
You're trying to say you see a contradiction, but you picked your sequences that you picked are not arbitrary enough. So in your case, you have two classes of sequences: one approaching from right and one approaching from left. This is saying I didn't say that they approach from right or left. 3 this says that xn goes to C no matter what direction. It has to be no matter what direction. So how do I get this proof? You will see as maybe so what I do, I braid the sequence. So then consider the sequence braided. So consider xn, so consider something like this. Consider x1 followed by y1, and then x2 followed by y2, and then x3 followed by y3, etc. Right? So because each subsequence, you see that I have the x's, they go to C, and the y's, they go to C. So any particular subsequence I pick still goes to C. So this thing will go to C. Okay. We can call this sequence just something like z sub n. Okay. So notice that z sub 2n is equal to y sub n, and z sub 2n minus 1 equals to x sub n. You see that? So if this sequence is the Zn, the braided sequence, then the even terms of the sequence, they are like y, and the odd terms of the sequence are like the x. So what do I know? So I know that f of Zn, that will go to somewhere else. By this condition, it will go to somewhere else. But if I take the even terms, that will go to the even terms go to p. Right? And so if the even terms go to p, but all the terms go to k, p and k are the same. And similarly, if I look at the odd terms, that will go to s, and so s and k are the same. And so the conclusion is that p equals s. Your function, here's what happens. You see, with your step function, you have a left-hand limit is 0 and right-hand limit is 1. But if you mix the two sequences, you have left, right, is not going to go somewhere. It's going to jump between 0 and 1. That's why it's not a counterexample. This condition is saying no matter how you pick the sequence, as long as the terms go to C, so they might go to C like sometimes from the left, sometimes from the right. You still have to get somewhere. Okay, so in your example, there are some sequences that don't go somewhere, and that's why the statement fails. But that's a very good counterexample. Cheer up. It's you should have seen the mistake I made over the weekend. I was almost crying. You cannot imagine how terrible it is. I wanted to say my Peking duck is cooked. Right? I had a very major argument. So many things connected. There's one detail that I noticed that I cannot verify that it's true. In fact, I think it's not. Therefore, everything I wrote that I spent the weekend writing completely useless. Throw it in the garbage. So that happens all the time.
Okay, but like wherever you want on X, if you come from the right or the left, you still can go to C, right? But if it's discontinuous at C, so there's cases where stuff is not true and it's still true.
Well, so we haven't yet mentioned continuity. We'll speak about continuity. That's just limit. Okay, that's just limit. So what I'm saying is this condition that any sequence. I don't. What's good about condition 3? In some cases, the limit is difficult and you don't know what it's equal to, but you just for some reason know that any sequence you take, you get a limit. There are cases, theoretical cases, where that happens. So condition 3 implies condition 2, because you see what you do is, what's L? L is all the possible limits that we have here, okay? So
it's not just something, it's the same thing. It's one thing.
yeah, so when it converges to something, that what we just verified, that if when we have this this condition, when we say to something, we might as well not bother saying to something. It's always going to be the same thing. So this will always be same thing. But you see, we stated something. We didn't assume, but it just the implication is that when I assume all the sequences converge to something, in fact, they always converge to the same thing. Okay, good. So we proved that 3 implies 2, right? 2 implies 3, 3 implies 2, and then I need to just go one more up. 2 implies 3. Okay. So I will erase this part. So finally, 2 implies 3. I mean, yes, sorry, 2 implies 1. What am I saying? Right, 2 implies 1. You get me, I hope. So 2 implies 1, and what do we know? So we know by assumption that whenever we converge to C, xn converges to C, f of xn will go to L. So my goal is to show that the limit of the delta epsilon is also L. Okay? So assume xn going to C such that xn not C implies f of xn going to some value L. L is the common limit. They all have the same limit. It's kind of like what we have here. We consider all those somethings. They all have the same limit, and that same limit, we call it P, S, K. All of it we can just label as L. All of it is the same limit L. F of xn goes to L. And what do we get? And that's what we have. So if no delta epsilon is possible, in other words, if I cannot force the full puncture neighborhood to map within epsilon, then there exists. Then there is. We can calculate delta. Then there is some xn that doesn't belong to L minus epsilon L plus epsilon when delta when we get delta of 1 over n. Because you see what delta means, no matter how narrow I make my input pipe, there are going to be always droplets getting outside those barriers, L plus epsilon, L minus epsilon. So what we have is that there is some x, I'm so glitchy, so xn not belonging to c minus delta of 1 over n to c plus delta 1 over n. There is an xn belonging to this set such that f of xn is not belonging to L minus epsilon, L plus epsilon. That's what I'm trying to say, right? So in other words, what am I saying? I make the pipe narrow. I can find a point in that narrow pipe, and that point is going to be a water droplet that lands outside epsilon. If delta epsilon does not work for my function, but condition 2 is true, so that's what I'm trying to find a contradiction. You see what I'm saying, right? So that means that I can narrow this pipe. Oh, this doesn't work. This delta of 1 over n doesn't work. So delta of 1 doesn't work, delta of 1/2 doesn't work. But no matter what size delta, I always get points leaking outside of this interval. So what does it mean? It means that xn, by this delta sub epsilon, this will go to 0, right? So the pipe is made narrow. It's going to 0. So that implies that x sub n goes to c. We also have that xn not equal to c. So that will imply that f of xn goes to L. But this is impossible because all the points are staying outside of this interval. So I hope that you follow me. You follow me? You see what I'm saying? So this delta of epsilon, I can make the pipe narrow and narrower. I can push the boundaries of the pipe to 0, and still some points will be squirted outside of that particular epsilon. But what it generates then I can take sample points here that are squirting out of the interval. And those sample points, they converge to C. But then the sequence of f of xn must converge to L. But it cannot because all the sample points are squirted outside of this boundary. So none of them actually enter this neighborhood. So that's a contradiction. In essence, what I'm saying is that condition 1, although it seems stronger than condition 2, and condition 2 seems stronger than condition 3, they are exactly the same strength. They can be taken as the definition of limit. They all give you exactly the same results. All right. So this is a theorem about continuity. Now, if we know the limit, we can state what is continuity. So maybe before I even state the continuity, that in R, I should make this remark. In R, we can consider a limit as x goes to c from the left of f of x. And that will designate it as f of c minus. Okay? Simply so we don't have to write this thing. And we also have limit as x goes to c plus. And that will be f of that, c plus. Okay? That's our notation. So the left hand and right hand limit. And they are defined in terms of delta epsilon accordingly. You just take the half pi. Okay? So for c plus, you just consider inputs from above c, or the inputs from below c, and you designate it as follows. Okay? So then we can make the following theorem. So theorem, so f is a real valued function defined in some neighborhood of the point C. So we have the following conditions. Then we have f is continuous at C, and that's by delta epsilon. Second condition is f of x sub n goes to f of c whenever xn goes to c. Notice that I no longer have the requirement that xn is not equal to c. It's important, okay? So if the function is continuous, I just drop the same requirement I had for limits, but I drop the requirement that xn cannot actually equal to c. It's now allowed to be c. And the third condition, and by the way, prove it again. We did it for the limit. Now you prove it for continuous functions just to see that you can actually, you understand those arguments. So that we have f of xn converges to something whenever xn converges to c. Notice again here, I drop the assumption that xn is not equal to c. That's very important. And a fourth condition, it's really because it's a real valued function. Fourth condition, f of c minus and f of c plus exist, maybe by delta epsilon, and f of c minus equal to f of c plus, which is equal to f of c. In a way, this is a statement of the first condition as you learned it in calculus, right? So, proof, try it out. We already did the same thing with L. Without looking in the notes, see that you can actually establish that all those results are true. Now, let's consider the following proposition, again something unique to real numbers. So we have let f be a function defined on the open interval a to b into R, be monotone. So in other words, it's either increasing or decreasing. For any C that is bigger than A, smaller than B, both FC minus and FC plus exist. Let's prove. So the function is monotone. Without loss of generality, it's increasing. So you know this statement. Without loss of generality, look, f is increasing. If it's decreasing, just multiply it by -1, and you have an increasing function, then multiply it by -1 again. Result of both. So f is increasing. What do we want to show? We want to show that a limit f. So we consider this. We consider the set A to be the set of all f of t such that t is less than c and bigger than a. That's my set A. And I will also consider the set B, which will be the set of all functions f of t such that c is smaller than t and t is smaller than b. So, what do you think? The function is increasing. What do you think is going to be the what's going to be f minus f of c minus? It's going to be what in terms of sets A and B? The function is again is increasing. Can you guess? Then f of c minus equals to. So I'm claiming, right? Then maybe I should write it claim. F of c minus equals, what does it equal? In terms of A and B. How is it equal? What are you doing when you take limit at c? I take the left-hand limit, I take t, and I push it closer and closer to c. The function is increasing. So as I push t closer and closer to c, f of t is going to do what? F of t will what? Increase. It will increase, and therefore, what's going to be the limit? You see, we must make it less than c. It's going to be what? What do I write here? In terms of A and B. Hangman, right? Supremum of A. Oh, do you see why, right? You move here, right? The function is increasing. Let me just draw you a tiny diagram, right? I don't know how C looks like. Here is C. here is A, here is B. What's going to happen? I'm going to increase. I drew a closed curve, right? But I'm going to increase. Maybe let's see I have, f of c is somewhere else. Who knows, right? That's why I don't allow t to equal c. So what's going to be the limit in here? It's really, if I push t closer to c, it's the same as actually looking to the upper bounds of A. To the least upper bound, in fact, okay? Now, how do I know that this is the case? Well, first of all, supremum of A exists because for any t belonging to the interval AC, f of t will be less than or equal to f of c, because the function is increasing, right? I'm not allowing c here, so A has an upper bound, or A is bounded above, okay, and has therefore a finite supremum. So take the least upper bound. So what you do is you show the following. So that implies that all f of t are less than or equal to supremum A. That's already clear. Okay? And if I subtract anything, so here what happens? Now, so I'll call this my my limit L for the moment. Okay? So how do I know that the function converges to L? So take L minus epsilon. Now L minus O, epsilon, not upper bound of A. Which implies what? Which implies that there exists, you know the symbol, it means there exists some T0 which is smaller than C and bigger than A, such that we have L minus epsilon less than f of T0, and this is less than or equal to L, because all of them are less than this L. It's a supremum. Yes? But the function is increasing. So what does it imply? This implies that for any, so maybe I should write since function is increasing, since the function is increasing, any t bigger than t0 and less than c will imply that f of t will be less than or equal to L and bigger or equal to f of t0, which is bigger than L minus epsilon. So what is our delta? The delta in this case is simply t0, well, it's c minus t0. Hence, if delta equals c minus t0, we have c minus t less than delta implies that f of t, so implies that L minus f of t less than epsilon. That's because it's increasing, I don't need the absolute values, you understand? So we are done. So our implication is indeed f of c minus equals to the supremum of A. Make sure you understand it. And another claim, which I'm not going to verify, it's the same. F of c plus equals to what? Infimum of B. So verify. same idea. If you understood what happened here, right? So what's delta epsilon? Delta epsilon, in this case, it's the left-hand delta epsilon, which means that I need to squeeze the pipe from the left. If I make the pipe from just the left part of the pipe narrow enough, all that left-hand interval will be mapped within epsilon to L. And that's happening here. You see, L is bigger than f of t, so I can just avoid the absolute value if I want to in this case. If you prefer, you can put absolute values. Not going to do anything. Okay, so what we just verified is that right-hand limit and left-hand limit always exist in a monotone function. So, next proposition. Makes me a little more worried. And in fact, this will be a theorem. So if f from A to B to R is monotone, then f has at most countably many points of discontinuity. So, in particular, if you you take more courses on analysis, you will study Riemann integrable functions. All monotone functions are Riemann integrable. As long as the measure of discontinuity is 0, right? There's going to be an entire theory on discontinuities. The set of discontinuities is a countable union of closed sets, by the way. Right? So you have all that stuff. But Riemann integration theory tells you that whenever the measure of discontinuity, that's roughly the length or the size of the set containing all the points of discontinuity, if the measure is 0, the function is Riemann integrable. And this is even better, because in this case, if it's countable, the measure will automatically be 0. If you understood nothing of what I said, that's fine as well. Proof? So what am I going to say? We already know it's monotone, so we know that it's left and right. It's left, and the limit on the left and the limit on the right exist. Okay. So what we show is, suppose that. So let D of f be the collection of points T such that f is not continuous at T. Okay? If let's have with analysis of generality, we again may assume that f is increasing. So the function is increasing. So what we show is this. So suppose that C and D, so let's say C and D were, C, D such that C is less than D are elements of this set. Okay? So then we consider the interval f of C plus, sorry, f of C minus to f of C plus. And we consider the interval f of D minus f of D plus. So those intervals are non-empty. We know that if f of c minus equals to f of c plus, the function will be continuous. So non-empty interval. So far good, you see that they are not empty. If the function is discontinuous at c and is discontinuous at d, it's monotone. So what happens is that this value has to be smaller than that value. If they are the same, then c is somewhere in between. You understand how discontinuity works? F of c is bigger or equal to f of c minus, less than or equal to f of c plus. Here is roughly a picture. So here is a point of, so let's say the function is increasing. Here is c, and here is d. So the function was increasing, and then at c, we have discontinuity. So how could it work? Maybe something like this. And then we reach d, maybe here, and then maybe could be that at d it's like this maybe. Right? That's an increasing function. You agree? It's going up, and then let's say this is my point c. So what is this bound here? So this is here f of c. This bound is fc minus, and this bound here is fc plus. Okay, so you can see that this interval cannot be empty, because if they are the same f of c, it has to be between f of c minus and f of c plus, will be squeezed to the common limit, and the function is continuous at c then. Now, what is f of d? Look at this here. It's higher. This here is f of d minus all the way to f of d plus. So what I'm claiming is, you see that the intervals are disjoint. This interval is going to be strictly above that interval, and then I can do the counting. So let's quickly try to notice that. So by taking t bigger than c and smaller than d, we see that f of t is less than or equal to f of d minus. So I should say it like this, that f of c plus less than or equal to f of t, which is less than or equal to f of d minus. You see, I put a point in between. This is t, and this point is basically the worst that can happen is that the red and blue boundary over here, they touch because of this calculation. You see this? So that means that f of c minus to f of c plus intersection f of d minus to f of d plus. You see, the most is that those endpoints are touching. This intersection is empty, which implies now. So we have a bunch of non-empty intervals. In each interval, I can put a rational number. Since intervals are disjoint, and each contains a rational number representative, we have that d of f is countable. the argument is finished. You understand the idea? So what we have is, we look at every discontinuity. We see that because we have an increasing function, every discontinuity corresponds to an open interval. And if I take two different points, I have two intervals that at the very worst, they just touch at the edges. So at the very worst, f of c plus is equal to f of d minus, so the open intervals are disjoint. You see? I know that simply by taking inequalities. You see that f of c plus might be equal to the point in between them, and this point, because d is bigger, d minus will be bigger than t, because d minus is approaching and is growing. So we see that those intervals are disjoint. And each interval contains a rational number. So I can count those intervals by rational numbers. Therefore, we have countably many discontinuities. It's finished. Right, we will continue next class.